Welcome to the CompTIA A+ 220 1101 Core 1 exam. This is Objective 2.2 Network Devices. If you walk in a data center for any organization, you'll find many different types of systems that are used for network communications. Sometimes these are single-use devices like this switch, or it may be a device that combines functionality. For example, the Soho routers that we normally use in our home are both switches, routers, and wireless access points all in one device. For the purpose of your exam studies, you should understand what these devices are and in what circumstances you should use these devices on your network. A router is a device that forwards traffic between different IP subnets. The router uses the IP address that's within the packet to determine what the next hop might be on its way to the final destination. Because this routing takes place at layer 3 of the OSI model, we often refer to these as layer 3 devices. And if we have a router that can be configured inside of a switch, you'll see those devices referred to as layer 3 switches. Although routers can certainly connect IP subnets that are using the same topology, it's also common to use routers to connect different types of networks together. For example, the interfaces on a router might connect LAN, WAN, copper, and fiber connections all in one single device. Another common infrastructure device is a switch. If you're using a copper cable to plug in a laptop or desktop computer, then you're commonly plugging directly into a switch. A router commonly forwards traffic based on the destination IP address that's within a packet. A switch determines where traffic should be forwarded based on the destination MAC address inside of that time frame. This is also a device that's able to forward traffic at a very high rate of speed because a lot of those forwarding decisions are based in the hardware of the device itself. Many switches have an application-specific integrated circuit, or an ASIC, which allows for very fast throughput. If you have a switch that's in the core of an enterprise network, there could be tens of, even hundreds of, interfaces on that switch. And many switches will also add additional power to the switch connection using PoE, or power over Ethernet. And as we mentioned earlier, if you happen to have a switch that has the ability to turn on additional routing functionality, we often refer to that as a layer 3 switch or a multi-layer switch. If you were to purchase a switch for your home from a local or online retailer, that switch probably doesn't have a lot of functionality. It is simply connecting all of these devices together. If you've simply powered the switch up and there's no configuration option on the switch at all, then you're probably using an unmanaged switch. Unlike switches that you might find in an enterprise, an unmanaged switch gives you the very few configuration options. For example, you can't configure any VLANs on an unmanaged switch. All the devices that you're connecting to an unmanaged switch would all effectively be on the same VLAN. There's also very little integration with other protocols or other devices. In an earlier video, we described the Simple Network Management Protocol, or SNMP. Network administrators often use SNMP to query devices on their network to check performance or any type of errors. An unmanaged switch commonly has no SNMP capabilities, so although you could connect to it on your network, there would be no way to pull or query information from the device. If you're purchasing a switch for an office or a larger organization, you're probably going to get a switch that is a managed switch. This is one that provides additional capabilities, especially for someone who needs to constantly monitor and confirm that this device is working as expected. For example, a managed switch may also allow you to configure different interfaces to be on completely different IP subnets, or what we call VLANs, or virtual LANs. These switches might also have configuration options to prioritize traffic. So you may be able to set voice over IP traffic to have higher priority than transfer of a file. It's very common for organizations to have multiple switches that they would connect to their network. And one way that you could prevent loops between all of those switches is by enabling Spanning Tree Protocol, or STP. To have STP as a configuration option on your switch, you probably need to have a managed switch. Some managed switches will allow you to perform port mirroring, where you can take traffic from one port that's on the switch and copy all of that traffic to a different port on the switch. Ideally, to plug in a protocol analyzer and be able to view all the packets on the network. This is pretty common for troubleshooting and packet analysis, and not something you would see on an unmanaged switch. If you're in the office or you're walking through another place of business, look at the ceiling and see if you see a device like this. This is an access point. It provides wireless connectivity for your local network. This is not a router that you might find in a Soho device that your small office or home office might have. This is a device that only provides a link between your wireless network and the wired network. You'll sometimes hear these devices referred to as a bridge because they are simply bridging or extending that wired network into a wireless connection. This is not a device that is routing between subnets. It's not performing any type of network address translation. It's simply bridging people on the wireless network to the folks that are on the wired network. An access point makes forwarding decisions based on the destination MAC address, which is identical to the way that a switch forwards information. The access point examines the destination MAC address and determines if that MAC address is on the wireless network or if it should send that to the wired network. One of the challenges with connecting many people in a work environment to the network is that there are a lot of cables that have to be managed. In this diagram, we have a number of people that are sitting at their desk on the floor of the building. And you can see that there are a lot of cables. We have a cable from every desk that's going back to the central wiring closet on the floor. In that wiring closet is a patch panel. We would connect all of these devices to the patch panel that run and is permanent. Once somebody is connected from their network to the desk to the patch panel, we don't need to move the cable going forward. Different organizations will have different patch panels. They will have a punch down block or a block in a closet that are filled with RJ45 cables, and it's relatively easy to move some of these cables to another patch panel if you need to move between networks. A lot of these cables are permanently punched down, moving from a desk to another wire. Some patch panels can be easily switched, and there's no tools that you need to patch one cable to another panel. A traditional firewall is able to allow or disallow traffic through your network based on IP addresses and port numbers. Since those TCP and UDP ports operate at layer 4 of the OSI model, it's common to refer to firewalls like this as an OSI layer 4 device. These days, it's increasingly common to see firewalls that understand application layer traffic, and in those cases, the firewall would be a level 7 device. Some firewalls can also act as an endpoint for an encrypted tunnel, which means that you can connect two sites together across a public network like the internet. But all of those traffic between those sites is encrypted. Some firewalls can act as a proxy. So if someone is browsing a site on the internet, the firewall will stop that communication. It will perform the browsing for the user, receive the response from that device over the internet, examine it, and make sure that there's nothing inside the traffic that may be dangerous or malicious, and then send the results of the query back to the user. And in many cases, this is what you would see at a SOHO, small office, home office. There are power over Ethernet cables that are injectors, and you can use them to power different devices. There's one wire for the network and one wire to power the device itself. It's pretty common to see on phones, cameras, wireless access points, and you may not be able to have a PoE switch available, so you may need to use an injector. So there's built-in power that uses in-spans, and then there's inline power that uses mid-spans. It's quite easy to find switches that have PoE. It will say it on the switch itself, and you will know if it's appropriate to use for those devices. Different devices need different types of power, and there are different standards for PoE depending on what type of switch you might be using. The traditional or original style of PoE is specifically called the IEEE 802.3 AF TAC 2003. This is the original PoE specification, has been rolled into standard 802.3 Ethernet standards. This provides 15.4 watts of DC power, 35 milliamps as the max current. So when this first came out, it was common to see it on VoIP phones and access points. But there became a need for more power for different devices. So there's PoE Plus, which is part of the same protocol, and it uses 25 watts of direct current and 600 milliamps. And later, we have PoE++, which uses 51 watts of 600 milliamps, or 71 watts that uses 960 milliamps. Before there were switches, we commonly use hubs to be able to connect all of our devices on our network. Sometimes you'll hear a hub referred to as a multi-port repeater. That's because hubs are not very intelligent devices, and any data that's going into the interface on this hub will automatically be copied and sent to all of the other interfaces on this hub. As you can imagine, it's not the most efficient way to communicate. And on top of that, we're not able to run any full duplex communications to a hub. So all of the devices plugged into this hub will operate at half duplex, which means it can only send and then wait and then receive. It cannot send and receive at the same time. So this is much less efficient than a switch, which can route and switch more intelligently. It's also limited to the speed with 10 megabits or 100 megabits, and quite difficult to find nowadays. It's rare to find this hardware. Next up on the legacy hardware are cable modems. This was used for broadband, for DSL, and different types of frequencies that we would send. The data on the cable network, we used DOCSIS, data over cable service interface specification. And these had high networking speeds at the time of up to 1 gig per second, which was pretty exciting. And if you're not connecting to the internet using copper cable or telephone lines, then you might be connecting to fiber. To connect to the fiber network, you need an ONT, or an optical network terminal, which is a device that's usually connected outside of your home or your premise. This is connecting an ISP fiber network and converting it into signals like copper or Ethernet that can be used inside of your home. The ONT is usually connected to the outside of your building, and it usually delineates the ISP's network from your own internal network. We refer to this as delineation, as a demarcation point or a demarc. Sometimes the demarc is located in your data center itself, or if you're at home, it's located on the outside of your home. It's important that a DMARC exists so you know what the responsibilities are for each different party. You know that any of the wiring on the inside of your house is your responsibility up to the point of the DMARC, and anything outside of the DMARC is the ISP's responsibility. Take a closer look at this ONT. This is the fiber connection coming from the street. You can see the fiber label is placed there, and you can see the device has outputs for data, which is an Ethernet connection. If you're going to connect a copper wire cable, it's going to be to a NIC. NICs stand for Network Interface Cards. They are the fundamental connection that every device needs that would be wired, like a computer, a server, a printer, a router, a switch, a phone, and etc. There's so many more. It's specific that it has to be an Ethernet connection. It has to be through the WAN, or it could use a wireless NIC as well, like a mouse or Wi-Fi. It's often built into motherboards when we do have this wireless connectivity, and there are many different options. You can use single port, you can use multi-port, you can use fiber as well. Okay, and we've come to the end of networking devices. Here's a pop quiz. Which device is the most limited? A, wireless access points, B, managed switch, C, unmanaged switch, or D, hub? And the answer to that would be a hub. We learned that hubs operate at half duplex. They can only send and then they have to wait in and receive. They cannot send and receive at the same time. And that's a huge disadvantage and makes it much slower than the other devices. Thanks for watching.